Okay, in this video we're going to look at something called a matched pairs design. Okay, which may sound confusing at first, but it's a very basic idea. And when we want to demonstrate that a treatment causes an observed effect, we use what we call a matched pairs design. We find the difference between the responses within each pair, then apply the sample T procedures to these differences. Okay, so this is kind of like a before and after thing. So if you look at like people in a weight loss program, you have a before weight for each person, and you have an after weight for each person. You make ordered pairs out of them, like a before and after. The difference between them, okay, will be a data value. Okay, so you take the before minus after, and that'll give you a data value that we can use and then apply the T procedures. Okay, so that's a matched pairs. Okay, so number 9, cola makers test new recipes for loss of sweetness during storage. Trained tasters rate the sweetness before and after storage. The sweetness losses, which is the sweetness before storage minus the sweetness after storage, found by 10 tasters are given below. Okay, so 2.0, 0.4, and so on. So whatever scale they're using, the sweetness before storage minus the sweetness after, a positive value will tell you that the sweetness before was higher than the sweetness after storage. Okay, so a positive value tells you that you started before at a higher value than after. Okay, so a positive value would tell you that the cola lost sweetness. Okay, so if we look at our values here, use the data to determine whether there's good evidence that the cola lost sweetness. Okay, so if we look at is there good evidence that the cola lost sweetness? Well, that means we're doing a hypothesis test. Okay, we're going to test a claim. Okay, so they're going to claim that the cola lost sweetness. So when you set up your hypotheses, okay, the null hypothesis would be that mu equals 0. Okay, that's basically saying that there was no difference before and after storage. Okay, the alternative will be that mu is greater than 0. Again, basically saying if you take the before minus after and you get a positive number, okay, that means that you lost sweetness. Okay, so after we have our hypotheses, we'll calculate our test statistic. Okay, T equals. Okay, these are just like before now. Now we have to find our mean and standard deviation for the sample. So we have a list of data. So in list 1, you're going to put 2.0, 0.4, 0.7, and so on. The sample mean is about 1.02. And the sample standard deviation is about 1.196. And again, I'm going to use several decimal values there, or decimal places, because those numbers are pretty small. Okay, so we'll use 3 or 4 decimal places for the standard deviation. Okay, so again, that's doing the 1 var stats on your list 1. Okay, so our test statistic, x bar minus mu divided by s over the square root of n. Okay, and we're using s because we're given the sample standard deviation came from our sample of values here. That means we're using the t distribution for our test statistic. Okay, so when you do the substitutions here, the x bar was 1.02 minus our hypothesized mean of 0 divided by s, which is 1.196, divided by the square root of n, which was 10. Okay, there's 10 data values here. So our t value for the test statistic, doing that arithmetic, is 2.697. So when you look at that on the graph of the t distribution, okay, mu being greater than 0 meant we're shading to the right. So if we look at 2.697, okay, the question is, or what we have to determine is when we make our decision, is that 2.697 too far away from the center of 0? Which is asking us, is the sample mean of 1.02, so if they lost 1.02 units of sweetness, whatever that's measured in, is that too far away from 0 to say that 0 was a faulty assumption? Okay, so with 10 data values, that's 9 degrees of freedom. And our alpha value, it didn't specifically say what alpha was, but when we say good evidence, now good evidence is in the eye of the beholder, okay, but I would suggest that good evidence means you want to be pretty sure, so we'll use alpha as 0.01, okay, to suggest good evidence. Now if you use 0.02, that would be okay. Okay, that's not something to focus on too much here. Okay, so when we look up an alpha value 0.01 in one tail or one-sided p, okay, so 0.01 in one-sided p, and there were 10 data values, so that means 9 degrees of freedom. So we go way up here to 9 degrees of freedom. That gives us 2.821. Okay, so 2.821 is to the right of 2.697. So what that's saying is the t-value of 2.821 has 0.01 area, or 1% of the data values to the right of it. So that is farther to the right than our test statistic. So when we look at, is our test statistic too far or too extreme from the center? Well, the answer there is no, because that test statistic is to the left of 2.821. Okay, so our decision is fail to reject HO. Which means if we fail to reject HO, then we cannot support the claim. Okay, so not enough evidence to support the claim that mu is greater than 0. Okay, so in the context of the question, we can't support the notion that the cola lost sweetness. Okay, we can't say that for sure. Okay, the next part here, explain why you should regard these results as only rough approximations. Okay, this is not something I go crazy with in the video trying to explain. Okay, which is why you need to read a book and watch the video, the stat tutor videos and all that. Okay, these are rough approximations because there's a small sample size. Okay, we don't know that the lost sweetness follows a normal distribution or not. Okay, they don't tell us that it's approximately normal, and we own a sample size of 10, so you need to be very wary of the results that we get here because it's such a small sample size. Okay, number 10. Okay, here's an example of a matched pairs where you're given the before and after weights of participants in a certain diet. Okay, so you have before and after weight. So when you go through and actually calculate the difference for these matched pairs, okay, you get five, 30, 15, and so on. That's just the before minus after. Okay, so we have a set of data values 5, 30, 15, and so on. Notice that when they start at 275 and after at 280, they gain 5 pounds. So that means that they had negative 5 pounds as far as the before minus after. Okay, so there, a negative isn't good. That means you gained weight. Okay. A positive here is good because that means they lost weight, assuming they wanted to lose weight. Okay, so we're going to test the claim that the mean weight loss of all participants is more than 10 pounds. So we're trying to claim that mu, the mean weight loss, is greater than 10. And we're going to use an alpha value of 0.01. So we have our hypotheses. The null is that mu equals 10. The alternative will be that mu is greater than 10, because that's our claim. X bar and S, we get those from entering the 5, 30, 15, 5, negative 5, and so on. Enter those in list 1 in your calculator. Do the 1 var stats to get X bar is 14, and the sample standard deviation is 13.238. Okay, what that probably tells you is, with a mean of 14 and a standard deviation almost as big as that, it probably tells you that this distribution would be a little bit skewed to the right, okay, or a bit skewed to the right. Okay, so we calculate our test statistic. Okay, so we're going to be aware of these sample results too, because we don't know that the weight loss, the mean weight loss, is normal distributed or not. Okay, so same thing as before. With a small sample size like this, you want to say the results may be a little questionable. Okay, you don't want to hang your hat on these results. Okay, so you calculate the test statistic. Okay, the test statistic we're using T because we don't know the population standard deviation, so we use S instead. Okay, the 13.238. Okay, so our T test statistic is 0.9065. Okay, we can see that that's not a very large value for our test statistic. But when we look at the table to find the region that has 0.01 to its right, okay, that's a t-score of 2.896. Okay, and you can find that in your table, 2.896. It has 1% in one tail. Okay, so the one-sided p-value is 0.01. Our test statistic, 0.9065, is closer to the center than that critical value for t-star was. So what does it tell us about the null hypotheses? Well, it tells us that our assumption that mu equals 10 was not a bad assumption because our sample mean of 14 resulted in a t-star value, a t's value, not t-star, a t test statistic of 0.9065, which is close enough to the center to say that 10 was a good assumption. Okay, so we failed to reject HO, which means there's not enough evidence to support the claim that mu is greater than 10. Okay, so in the context of the question, we cannot say that the mean weight loss for the participants was more than 10 pounds on average. But again, these results, there was only a sample size of 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's only 9 in the sample. We don't know that the original was approximately normal. So again, just like before, we had a small sample size. So there are only rough approximations as far as our conclusion here. Okay, a better hypothesis test would be if you had n greater than or equal to 30, because then you look at the central limit theorem. Okay, but I don't want to give you 30 values in a list. Okay, so a better test, again, would be to increase your sample size so the central limit theorem does apply, and that would allow you to have more concrete results rather than just rough approximations. Okay, so those are two examples of matched pairs design and using the t-distribution with those.